Hey guys, I'm just going to wait until everybody logs in and then we will start our lesson. And so we're going to take a few minutes where I'm just going to be sitting here and smiling at the camera. And then once I know that you are all logged in, we will get started with today's lesson. Jordan, if you are able to watch this right now, since I see there's one watching, if that is you, Jordan, I do need you to type your name in the live chat because I can't really hear from you until you type into the live chat section. So please type into the live chat, just type in your name, and I'll know that you are actually watching. I'm talking to Jordan, I'm talking to your mom, trying to figure out if you are on this lesson. Emily, I thought you were doing a snow day. Emily, I thought you were doing a snow day. Emily, type in your name and type in if you can hear me. And I hope you have a fun time when you do go, but welcome to the class. It's good to have you. It's my pleasure. Alright, I don't know why it won't let you sign in to chat, so what I can do for Jordan is you can just text your questions while everyone else is putting them on the live chat, and that would work just fine. I noticed that so far only Emily C is on, and we're missing Emily Mongold, I think. So we do have Jordan and Emily, but we are missing one Emily. It does say 3 people are watching though, so that might be my other Emily. And so Emily M, if you are watching and cannot live chat, if that's not available to you, text me, because apparently Jordan's not able to do that as well. And I'd like to get started so that we're not just sitting here staring at each other or staring at the screen in awkward silence, because that's awkward. Emily, technically we would have been better to have read 8.1 before starting this video, but that's okay. I don't think any of you guys have read 8.1 yet, so you'll just have to read it after this lesson and watch the videos that we already have on Edpuzzle. So you are still going to go back through and watch those videos. Really what I'm going to try to do in this video lesson is give you a precursor and also go over some things that I think you may have questions about when you do get around to watching those videos and reading the chapter. So it's okay that you haven't read the chapter yet, or potentially haven't watched the videos yet. We'll get you caught up, that's fine. Alright, in 1 minute, it's going to be 1 o'clock, and I'm going to start the lesson as if Emily M is watching, because we had agreed that we would start at 1 o'clock, and I don't want to hold anybody up, and I know the Emily C is trying to get out and spend some time with her family. So I will start, and then Emily M, if she's not able to watch this, can always rewind it and watch it afterwards, so that would be fine. But I don't want to sit here in awkward silence anymore. So we will start exactly at 1 o'clock. I know. So that means I'm going to just go ahead and get started, and that is fine. I have jury-rigged some things together so that we can have this be effective. For instance, I found little magnets, and I made this cookie sheet. And so now I can show you electrons as they bond so that we can talk about this covalent bonding as if I have a whiteboard, which I don't have access to at home. So instead of writing on the whiteboard, I will use that to try to represent the covalent bonding. The first thing that I really want to stress to you guys is the fact that covalent bonding is sharing. Remember that last chapter, ionic bonding was all about taking. For instance, one atom like lithium would have maybe one valence electron, and then another atom like chlorine might have 7 valence electrons. And both of these atoms are not happy or satisfied the way that they are. So what would happen is the, yay, welcome Emily. Alright, so what would happen is the chlorine would end up stealing the electron from lithium, which would make lithium be +1, a cation, and then your chlorine would become a -1 or an anion. When that happened, they would get close together and they would bond ionically. And remember that that ionic bond is that electrostatic force holding those two atoms together because one is now positive and the other is negative. That's an ionic bond. In this chapter, as we start chapter 8, we're going to learn about the other type of bonding. And this one is going to be a bonding where you're sharing. If I had you in class, I would definitely make you do an awkward example that you would be able to help remember this type of bonding, because if I had you all together, I would have you guys be in a healthy relationship instead of in the unhealthy relationship where one of you stole from the other one, like they stole their heart. And so in the other one, you would have them share the heart and you guys would be in love, but this would be a covalent bond. So, covalent is sharing, ionic was stealing. I guess that Emily is also on now, and I don't see Emily as on the chat, but that's fine, Emily. What you have to do is just text me, I guess. And if you can see this video, I want Jordan and Emily to send a text on the group chat with your parents, and just send a text saying, I am able to watch this video, because I know that you both are now logged in, and all that I needed from you guys with the live chat was to be able to get your feedback so that you guys could answer questions and things like that, so that you guys could ask your questions and I could answer them. Alright. And I'm glad that you read it a few weeks ago, but now we're going to remind you of it. Alright, so the first thing, I need you guys to have your books out and open them to page 240, and we're going to just kind of look through a few things that are in the books. So have your book, have it open to page 240, and we're going to start there. They start when they explain covalent bond by talking about why atoms are bonding. And we have to go back to chapter 6 where we were talking about, and chapter 5 even, where we were talking about our valence electrons and how atoms really would like to be stable. So if you remember about our valence electrons, we went through and we talked about whether they had electrons in the 1s or the 2s or the 2p and then the 3s and so on and so forth. And we always were labeling those and showing where those electrons really live in the sphere or the dumbbell or the clover. And when we were talking about that, we identified the outermost shell, the highest quantum number, that was considered our valence electrons. And so we, if you remember, talked about how in group 1, and I have my periodic table, so I'll grab that. Everything that was in group 1 actually had one valence electron in the outermost shell. Yes, Marcy. Hi. Oh, that's fine. If she can she watch the video? Is she watching right now? Oh, that's the wrong video. If James is on it, you want to go and find the other one. I'm live right now. You're actually on this video now, and it should be Janet Sanders Church Chem, and I am right now in the middle of the live feed already. Okay, so are you guys able to see this live feed? Great. No problem. Now, is she going to be able to respond to the chat now? Because if not, just have her text me her questions. That's fine, because I have my phone right next to me, too. I see her. All right, we're all good. All right, no problem. Bye. Welcome, Emily. All right, so we were just saying that in group 1, we remembered that there was 1 valence electron. Group 2, there were 2. And we're going to skip our transition because remember those could have more than 1. And then in group 13, we had 3. 14 was 4. 15 was 5. 16 was 6. 17 was 7. And then 18, except for helium, had 8 valence electrons. So if that is what we wanted to remember, jumping into why do atoms bond covalently? So unlike ionic bond, where I've already said you have a trading of electrons, where one is stealing the electron from the other, in a covalent bond, what they're going to do is they're going to share. Now, I would like to point out, this does not happen between metals and nonmetals. This is going to happen between your nonmetals. So in your periodic table that I just had out, it's all the yellow ones. These guys right here. They're going to bond together, and they're not going to be bonding with metals, which is one of the ways you can tell that you have a covalent bond and not an ionic bond. Because in an ionic bond, you'll have a metal and a nonmetal. In a covalent, it's just going to be those nonmetals together. So essentially what's happening is they're going to try to gain stability by getting to 8 valence electrons, and that's the important part. I know that Jordan's not able to use the chat, but Jordan is able to use your messaging, so I am able to see Jordan's questions. So we are all here, we're all working on this, and we're good. And I'm now very popular because I'm getting calls from other people too. We're going to ignore that though. Alright, so notice that in page 241, we should all be there. You see that a covalent bond is where they're actually sharing those electrons, and you're going to call things that are bonded covalently molecules. It is going to be important to remember this term. The diatomic molecule is where you have 2 of the same atom bonding together. So if you have Cl2, that's 2 chlorine atoms and they're bonded together. You are fine, Jordan. Alright. It's so much harder to keep your train of thought when you're trying to read the text, so I'm a little bit more scatterbrained than I would have been in class, but that's okay. We're all just working through this together. So the next thing that you're going to see is the single covalent bond. And so I'm going to use my improvised atom, and I'm going to turn this, and you guys are going to see what happens when you have a single bond. So if we have 2 things that are in group 17, so those are going to have 7 valence electrons, and these are going to represent your electrons. This is your atom, the nucleus. So I'm going to try to make these stay. There. So notice how around this atom there's 2, 4, 6, 7 electrons. And then around the other atom, we're going to put the same thing, 7 electrons. Alright. Oh, my electrons aren't wanting to stick. Alright, you know what? That atom's misbehaving. So there's 7 electrons around. Sorry that they're not quite staying, but we're going to say that, you know, there were 7, there's 2, 4, 6, and then there's the 1 here. So when we have a covalent bond, what's going to happen is these 2 atoms are both going to not have enough on their own. And when they get close to each other, the extra electron that's not paired is going to be donated or shared between the two. And so they kind of just go in the middle between the two atoms. And what happens when they're in between the two atoms is you have a single covalent bond. So this atom right here gets to count both electrons. Notice that one of the electrons came from this atom and one of the electrons came from this atom. So that's what's happening, and they're sharing the electrons with the other one so that they can count the electron. So notice that this atom gets to count 2, 4, 6, 8. And so now this atom is going to have a complete octet. This atom over here, which has fallen apart, so I'm sorry about that, would have 2 electrons up here, 2 electrons right there, 2 here, so that's 2, 4, 6, and then it gets to count both of these as well. So this atom also gets to count it as having a full octet. So that's why you have a sharing of electrons going on. It's so that both of the atoms get to consider themselves full and having a full octet. So that is a single covalent bond, and a single covalent bond means that each atom is donating 1 electron, and they have 1 single electron pair shared between the two of them. All right. Now that's not the only way that atoms bond. When they bond, you can have more than 1 single covalent bond. And I'm going to try to use my paper now because that was kind of hard to do. So I'm going to use paper and I'm going to draw if you have more than 1 single covalent bond at a time. So if you have something from group 16, I want you guys to type. I'm actually going to, oh yay, Jordan actually is on the chat now. I'm going to ask you guys a question now, and I want you to tell me how many valence electrons would something from group 16 have? So go ahead and everybody type it in, and I'm going to wait until you answer. And I'm going to draw myself an atom while you are working on that. I've got an answer from Emily. I've got an answer from Jordan. I'm missing the answer from Emily M, but we're going to go ahead and go on. You are correct. It is 6. So notice that I have oxygen, which is an oxygen is going to be an atom from group 16, and I'm trying to draw this as the nucleus, and there's the element oxygen. And so around the outside of it, notice that when you are putting your valence electrons, actually go around and fill all of the outsides before you start doubling up. So we're going to pretend that each element has like an imaginary box drawn around it, and we're going to have to go and put an electron here at the top of the box, then at the side, bottom, bottom, and then we go back and we start doubling up. So this is 1, 2, 3, 4, 5, 6. So notice that we didn't double these 2 single electrons. We didn't put them together as a double right down here, because we're going to have to work on bonding this in a second. So that's actually the proper way to draw this. And so always try to go with, if you have 6 electrons, or if you have 5 valence electrons, or if you have 8 valence electrons, go around the outside 4 corners of your symbol. So you would write down O or C or whatever, and then go around the corners of that, putting your electrons until you have completely filled it. And that's fine. Our internet connections are going to make it so some of us have worse lag times than others, Emily, so it's okay. We'll all still be able to answer. Yes, you're not allowed to double the electrons until all 4 spaces are filled, so that's correct, Jordan. So now what we're going to say is, if this atom were to go near something that's from group 17, how many valence electrons would something from group 17 have again? And I want you to all type it in. So if something was from group 17, let's say chlorine, how many valence electrons would you have? Go ahead and type it in. Jordan is correct. So is Emily. All right, and I'm sure Emily M is going to be there in just a minute. So notice that we have chlorine, and I didn't actually put a circle around chlorine because I realized that was probably going to be confusing, so I'm not trying to draw the nucleus. I just have the symbol chlorine, and I started here and I went 1, 2, 3, 4, 5, 6, 7. And so I have 7 electrons around. Now, notice what's going to happen. What do you think is going to happen between oxygen and chlorine when they both have 1 electron that they want to share? What are they going to do? I'm waiting for somebody to type it in, but I don't know if you guys caught that. There you go, Emily got it. They bond. So what happens is these 2 atoms are going to share 1 electron with each other. And so we draw that as a single line between them. And a single solid line represents 1 single bond. That means we are sharing a pair of electrons. And just like you have a pair of shoes, that's 2 separate shoes, in 1 pair. This line represents a pair of electrons, so it means that you have 2 electrons being shared between oxygen and chlorine. Now, chlorine, let's count for chlorine and see if chlorine is happy and satisfied now. Chlorine has 2, 4, 6, 8. 8 electrons, so chlorine is now satisfied. What about oxygen, though? Count it for me and see if oxygen is satisfied with bonding with just 1 chlorine. So let's see oxygen. We've got 2, 4, 6, 7. So what's wrong with this? And your answer should be oxygen's not happy yet. So if there's chlorine floating around, there must be another chlorine somewhere nearby. And so what do you think is going to happen with the next chlorine that comes near this oxygen? Yes, it is unstable because it only has 7, so it needs to have more. It needs 1 more chlorine. Good, so go ahead and on your paper draw another chlorine. And again, I'm going to try to do this while watching you guys so that you guys can see. I start by going, 1, 2, 3, 4, and then I want to leave this one open, so I'm just going to go 5, 6, 7. So that's 7 valence electrons for chlorine. And notice how this 1 lone electron and that 1 lone electron are going to be able to be shared between this. And so notice that you have another single bond right there. The important part here is you're sharing 1 pair of electrons between this oxygen and that chlorine, and then another pair of electrons between this oxygen and that chlorine. So this is not just 1 single bond, it is 2 single bonds. And so you are able to have more than 1 single bond forming between your elements. Alright, so now I'm going to set up another one. And in this example, I'm going to have something from group 15. So let's go with nitrogen. How many electrons, how many valence electrons does nitrogen have? Go ahead and type that in for me. It does have a healthy relationship because they're sharing. They're both sharing the electron. Emily Mongol, don't worry. It's okay. As long as you're still getting the information, you're going to be okay. Also, you're getting this almost as if it's like happening right then. So the lag is just keeping you right in the loop. You're good. Alright, so I see... Don't worry, Emily, we will do the awkward thing showing the bonds in our covalent love relationship. We'll still do that in class. It's just going to have to be on Tuesday because it makes it so that you guys remember. Like, I promise you, if you have to act like you are sharing your heart like a shared electron pair, you're going to remember covalent bonds so much more. It's just the awkwardness makes it make more sense for some reason for kids. Alright. Alright, so nitrogen has 5 valence electrons. I know that you guys got carried away with the laughing there. We didn't really answer the question, but that's okay. Nitrogen actually only has 5 valence electrons, like that. So I'm going to pose a question for you guys. Oh, Emily Mongold got it first. Good job, Emily. Here we go. If you only have 5 valence electrons, and you have something that's going to be, the nitrogen is floating near something from group 17 again, how do you think this is going to bond? And I think you guys can answer this without me drawing it out. So just think, and I want you guys to see how many of the things from group 17, we can just say chlorine again, that's fine. How many chlorine atoms is nitrogen going to need to bond with in order to be stable? Emily, you got it first. Yes. So notice that we're going to draw, and go ahead and on your own, each of you draw, and good job, Jordan, you got that as well. Go ahead and draw 3 chlorine atoms around the nitrogen and how they each have 7 valence electrons. This is much easier than playing with the magnets, by the way. That worked so much better until I went live, and they were sticking beforehand, but once I went live, they started sliding off the cookie sheet, and so it didn't work. Alright, so here's my nitrogen surrounded by 3 chlorine atoms. Notice how each chlorine atom has 1 lone pair electron, and by the way, the electron that's all alone, that's called a lone pair electron because it doesn't have a partner, it doesn't have a friend. So notice that now you have nitrogen and it's surrounded by 3 chlorines, and each of these chlorines is willing to share 1 electron with your nitrogen. But nitrogen wouldn't be happy if it only shared 1 like this. It'd still be, unsatisfied because it only have 2, 4, 5, 6 electrons. And so it has to do 3 single bonds like so. And so now your nitrogen has bonded 3 separate single bonds between each of your chlorine atoms. Yes, and so each chlorine only shares 1 electron with your nitrogen. And the reason that they only share 1 electron is because they only have 1 valence electron that's lone pair. They already have, if you think about it, chlorine already was full with 2, 4, 6. These guys already had pairs. It just had 1 that wasn't paired, so it only had 1 to donate or 1 to share. It didn't have more than 1. Alright guys, so that is talking about single covalent bonds. A single covalent bond again is where you share how many pairs of electrons? I don't know if you caught that was a question. In a single covalent bond, how many pairs of electrons are being shared in a single covalent bond? And remember, a pair means 2. So Jordan, I'm going to say, okay, you are saying 2 electrons are shared. I understand that that is what you meant by that, so that's good. So 2 electrons are being shared together. That's called 1 pair because, remember, the 2 together is 1 pair. So in a single covalent bond, you have 1 pair of electrons, which is 2 electrons. Alright, that matters because now we're going to go on to talk about a double covalent bond and then a triple covalent bond. So as we get into a double covalent bond, what do you think is going to be different from a single covalent bond where you're sharing 1 pair of electrons, and then when you share a double covalent bond, how many pairs of electrons do you think you're going to share with a double covalent bond? Alright, Jordans, help me out. When you say 4 pairs, do you mean 8 electrons or do you mean 4 electrons? Emily, good job. Because I think, Jordan, I think you're thinking the right thing but putting the wrong term there. Got it. Okay. It's 2 pairs of electrons, which is, if you're going to say it this way, you can say 2 pairs, or you can say 4 total electrons. So I understand that you say 4, so say 4 electrons instead of saying 4 pairs of electrons, because 4 pairs would be 8. That'd be, 1 pair, 2 pairs, 3 pairs, 4 pairs, so 4 pairs is really 8 electrons. And I wasn't trying to be Spock there. Spock moment. Yes. Alright, so as we get into double bonds and triple bonds, we're going to find that sometimes atoms can share with another atom. They don't have to just share 1 pair of electrons. Alright, so let's go ahead and look at something from group 16, but I don't want to do oxygen. Let's do sulfur. So please, on your paper, draw sulfur, and it's from group 16, so how many valence electrons will it have? Notice that group 16, it has 6. Group 16, not group 17, so Emily, it's going to have 6 valence electrons, so be careful about that. Remember, if it's in group 16, it only has 6 valence electrons. And let's just say that you have another sulfur floating around nearby. Yes, group 16. So notice that you have 2 sulfurs, and each of them has 6 valence electrons. Well, if they're near each other, they're going to be willing to share, right? So if you have this, 1 pair can be shared right here. So that's it, starting with our first single bond. But notice that each sulfur has another lone pair electron, and it's not full. They're going to have 2, 4, 6, 7. So instead of trying to find something else to bond with another single bond, couldn't they just share these as well? And the answer is yes, they can. So they're going to share both pairs with each other. So this is not just 1 pair of electrons, this is 2 pairs of electrons being shared between your sulfurs. 1 pair here, 2nd pair there. Now, don't get confused with the term. If you're saying pairs, you mean 2 electrons, alright? So if you're talking about how many electrons are being shared overall, there's 4 electrons being shared overall, but that's 2 pairs because a pair is 2 electrons. Just like a pair of shoes is 2 shoes. Alright, so that is how that works. That's 2 pairs of electrons. When you have 2 pairs of electrons between the same, 2 atoms, this atom is sharing actually with this one 2 pairs. That's called a double bond. Now I want to point out the difference. Over here, notice how oxygen was bonding with this chlorine and with this chlorine. But between each atom, there was only 1 pair of electrons. There's only 1 pair being shared here and 1 pair being shared here. That's why this is a single bond. It is not a double bond. It's 2 separate single covalent bonds. Whereas here, between the same atom, this atom and this one, it's sharing 2 times. It's sharing 2 pairs between the same atom. Alright, so that's why this is a double covalent bond, and the other one was 2 separate single covalent bonds because it was with 2 separate atoms. Alright, now I'm going to throw in an extra term for you. It's going to be sigma bond and pi bond. A sigma bond is going to be the first bond that you have. It's always going to start out with a sigma bond. It's just the name for the first bond that forms. So when you looked back here, this one, the first bond that formed right there, that's a sigma bond. This one, right here, that's another sigma bond. This one has 3 sigma bonds because there's, the first bond that shares between 2 separate atoms. When we go here, notice that we had 1 sigma bond because that was the first bond that was happening, the first bond that was being shared, but we have a term for the second bond in between 2 atoms. The second bond is called a pi bond. I like to remember pi bond because in Thanksgiving and Christmas, what do you always want seconds of? And if you said turkey, you're wrong. The answer is pi. You want more pi in Thanksgiving and Christmas. You always go back for seconds on pi. So that is why your pi bond is the second bond, is because it's the second one. Yes, good job, Jordan. You always go back for more pi. All right. So now what we're going to think about is, well, if you can have a double bond between something, so you have 2 pairs of electrons being shared, what would happen? I know, but just pretend you do, because it makes it make more sense, right? If you didn't say pi, then it wouldn't make sense to have this be called a pi bond. All right, so now what we're going to have to think about is what happens if things need to share, like let's say we had nitrogen again, which nitrogen had 5 valence electrons. And so notice that if you have 2 nitrogens that are near each other, and each of them have 5 valence electrons, they're going to end up sharing, just like the sulfurs did. They're going to go, hey, let's share this one. So they start with the first bond. But then they go, hey, we still need more electrons and you're still willing to share, so they're going to share this one. And then they're going to also share this one. And because that's really sloppy, I'm going to redraw it, okay guys? So I'm going to redraw this with the 3. There you go. So the nitrogens are now full, because notice that they have 2, 4, 6, 8. So this guy's happy. And then this one has 2, 4, 6, 8. 8 electrons. And so they both have 8 valence electrons, and they're both satisfied. So what I'm going to ask is, what do you think this kind of a bond is called? If this one was a double bond, and this one was a single bond, what's this one called? Jordan and Emily are correct. Let's wait for the other Emily to chime in because her lag time is a little longer than ours. And Emily, I don't know if you're still there and able to answer, but I'm going to go ahead and start going on. It is a triple bond. Both Emily and Jordan got that one. And so we're going to go ahead and continue working. Oh, there you are! Yay! Triple bond is correct. And I like your smiley face. I mean, really, that's all this first chapter section is doing. Joel's awake. I'll be right back. No ball. Alright guys, really quick, just say hi to the cuteness. Say hi, Joel. Yeah, say hi.
Wow.
Yeah, wow.
Oh, yeah.
Yeah. Okay, so we are almost done. I know. He misses you too. Say hi, Emily. Say hi. Yeah. Well, we are almost done with this chapter anyways, the first section at least. The idea was basically to really make sure you guys understand that covalent bonds is where you are sharing electrons. And the reason you share electrons is to make a full octet. And so that was the whole point of this. So I do think that you guys have that to start. And the fact that you had single, double, and triple covalent bonds available. I'm going to try to ask you a quick question before we go on and talk about the last little bit. I think that Joel has made it so that we are very much off topic now. So, I'm going to put him down. Say bye-bye. Bye-bye. Oh, come on. Say bye-bye. You know how to say bye-bye. Say bye-bye. Alright. I'm going to let him go play. Oh. Or not. Okay. Well, my question to you guys before we go on and finish up this lesson is, what do you think would happen if you have two things that are in group 14, and those two things that are in group 14 come close together and are able to bond? What do you think you might form then? Yeah, but you can't write on the book, baby. How about you write on the paper? Go ahead. Emily, I believe you got it. Good job. Quadruple bond is what I would call that as well. Because you would have 4 pairs of electrons, each of them sharing between. So you would have four pairs of electrons being shared. Good job. Alright, that brings us to the last thing that we're going to talk about before we go, which is the relationship between bond length and bond strength. Alright, so that's on page 246. So page 246. And I'm going to draw. I know Joel has just made my notes that I had beautiful. So we're going to redraw on the next page some bonds for you. Alright, so here we have our length versus our number of bonds. Notice in a single bond all the way at the top, you have a longer length between the bonds because they're only sharing 1 pair of electrons, so they're able to be spaced out more. Here, you have a double bond, and you're going to have them be closer together. The 2 atoms are actually a little closer to each other. Then here you have a triple bond where you have 3 pairs of electrons being shared, and because they have 3 pairs of electrons being shared, they have to be really close. And so notice as the bond number increases, your bond length decreases. So as the bond number increases, the bond length decreases. And think about this. Electrons are both what kind, all electrons are what charge? No, okay, let's draw on this page. This page. And you guys know what charge electrons are. I know this seems like it's random, but it's not. Good. They are all negatively charged. Think about 2 gigantic, strong magnets, and if you take the negative side of one magnet and the negative side of the other and try to push them together, do they like that? Are they going to easily be pushed close together because they are both negative charges? Yeah? Yeah. correct. They don't want to be close together, right? Opposite charges attract, but the same charge repels. And so if you're trying to make two really strong magnets go closer together on the negative and the negative charge, they're going to repel, and you're going to have to be really strong to force them to get closer together, right? That's the same thing here. You have to be really strong to force those electrons to be so close together. You are essentially making them be near another charge that's the same as them. And that's really hard to do. So which of these three do you think is the strongest kind of bond? Because they're, if you think about it, they have to be that strong because they are that close. So which of these three would be the strongest bond? You can say single, double, or triple. And Jordan's got it right. And yes, poor atoms, because they have to be squished all close together. So yes, the triple bond is the strongest because it is closest, and you know that if it's closest together, it's making those negative charges be so close to each other, and they don't want to be close to each other. They want to be as far apart as possible. And so the fact that they're in nature, you can actually see them. They're actually closer together than a single bond would be. So that's the strongest bond we have, is the triple bond. Or, in the case of something from group 14 and 14, that would be a quadruple bond. That would be even stronger than a triple bond. Alright. We can find our chapter. Oh, there's one last thing in here. I'm sorry, guys. I thought I was going to get to let you go. Endothermic versus exothermic reactions. Well, most of you already know endo and exo. You know what that means. Hey, don't get fussy. Smile. Smile, Bubba. Alright. Endo is going to, and yes, Emily, you are right. Endo means inside. Exo means outside. So essentially with these terms, you're talking about endothermic and exothermic. Bless you. Oh, bless you. Yes, I agree, Emily. It is kind of ironic. Alright, so endothermic reactions are ones where as you rearrange the atoms, so remember, in this you are taking two atoms and you are bonding them together and they are going to share electrons, right? In a chemical reaction, you're going to have that happen. You're going to have bonds be broken and rearranged and formed, and essentially you have two options as far as heat, or the overall energy of the atom. In the end, you have two options as to what can happen. One, when you're done, you could have more energy than you started with, and it could need to get rid of that energy by giving it off or sending it to the outside. That would be an exothermic reaction where they're sending heat out. Or you could have less energy than you started with, in which case you'd need to suck energy in order to get back to the energy level that you wanted to be at. And those ones are endothermic because they are taking energy into themselves, or heat into themselves. So when you feel like an ice cube, you're feeling cold because the energy is going from your hand into the ice cube. So that's an endothermic reaction. And yes, he really likes this pen, and he really wants to be able to draw all over my chemistry book, which I don't want him to do. So we're trying to keep it on the paper. But that's the difference between an endothermic and an exothermic reaction. So if you're thinking about it, the reaction will either have more energy at the end than it started with, or it will have less energy at the end than it started with. Alright. That's really all that we really need to cover for this first section. On Tuesday when we meet in class, hopefully, because we will hopefully not have snow anymore on Tuesday, or if we have it, it won't be as bad. What we're going to cover on Tuesday is section 8.2, so I do want you guys to watch the videos for 8.1 and 8.2 and do the reading for 8.1 and 8.2. I also would like for you guys to do a little bit of homework for me. I know you guys all go, no homework, but what I'd like you to do is not that hard. I want you to practice on page 244 how it says the practice problems and it asks you to draw the Lewis structures for each of these molecules, and it gives you 5 molecules. I don't want you to do the challenge problem. I just want you to do numbers 1 through 5 on page 244. So go ahead and draw those and bring that to class on Tuesday, and hopefully we will see you then. But otherwise, it's been a really great lesson. I am glad this worked out so well. I hope it helped you guys. He is now stabbing the page. So here's his beautiful artwork from Joel. How about you go ahead and draw that down here? Yeah, go ahead. Take it with you. Draw, baby. Alright. And I'm going to wait a couple minutes and see what your comments are. And if you have any extra questions that weren't covered thoroughly enough, please feel free to type them in and I will answer them before I actually stop this live feed. But otherwise, it's been a pleasure, and I hope you guys enjoy your snow day. And Emily, yes, you still have to watch the 8.1 videos. I know I already said that, but I'm just now reading your questions. It's my pleasure. So now that I know, I could have just put him down with the book and the pen and he would have just been fine. I will. So here's what I want to know. Can you guys see each other's questions when you're doing the live chat? It's my pleasure, Emily. Good to know. Bye. Alright, since there's no extra questions, I'm going to stop streaming. And again, I hope you enjoy your snow day.